recorded then, or okay,
Yeah.
perfect.
So, okay, there we go. Yeah,
There we go.
screen's looking good. All right, so welcome everyone to the One World Combinatorics on Words seminar. We're very pleased to have Curtis Bright from the University of Windsor today, and he's going to talk to us about mathematical problems with satisfying solutions.
Mhm. Thank you, Narad. So yes, I'm Curtis. I'm going to be talking about some mathematical problems that have some satisfying solutions. And satisfying here is a bit of a play on words. It's going to be solutions based on what we call a SAT solver. So normally I'd ask the audience for a show of hands for if they've even know what a SAT solver is, but essentially it's a classic problem in logic where you're given a logical expression in Boolean logic, so all the variables are just true or false, and then you're asked, can you make the expression true? So we have our standard logical connectives from Boolean logic that you may uh, remember. You have and, you have or, you have not, you have implies. These are the ones we'll be using. And so let's just actually just go over a simple example here. I want you to think about this. Let's say we have the expression x or y, and x implies not z. Now, can we make this true? Can anyone say if this can be made true or not? So if you post it in the chat, maybe Narad can read it out. Is there any?
Yeah, I'm happy to read out answers if anyone writes something in the chat.
So if you think about it
Shepard
here,
says,
right?
of course.
Of
Seven says, of
course,
course.
yes, yes. So and how would we do this, right? It actually there's multiple ways of making it true. One way, I mean, so when I look at this, okay, x or y, well, let's just make x and y true. That's going to make the first part true, right? So then when you come to the second part, if x is chosen to be true, then this implies not z has to be true, which would imply z is false, right? So this is just one way to do it. We take x and y to be true and z to be false. Okay, so this is the SAT problem. Given a logical expression, make it true, or tell me that it cannot be made true, right? So if it can be made true, that's called satisfiable. If it cannot be made true, that's called unsatisfiable. So SAT is a very well-studied, important problem, both in theory and in practice. And you don't have to take my word for it. There's no better person's word to take probably than Donald Knuth, right? So Knuth is, one of my heroes. He's a very prolific computer scientist. He's been writing his magnum opus, The Art of Computer Programming. And I actually looked this up. It's kind of astounding to me. He's been writing it for over 60 years, right? He started in the early 1960s, and he's still going strong, right? He's absolutely amazing output. So the last volume in The Art of Computer Programming, 4B, came out 3 years ago, and it's literally 700 pages long, right? And just to show you how important SAT is, or at least how important Canute thinks SAT is, he devoted a full half of that book. The second half of that 4B is totally talking about SAT, applications of SAT, how to solve SAT, so algorithms for SAT and so on. And I won't really talk about the theory so much, but there is an interesting dimension to the theory. Essentially, the conventional wisdom is SAT does not have any provably fast algorithms, right? The best algorithms are conjectured to run in exponential time. We certainly don't know of any, say, polytime algorithms for SAT. And yet, that said, the surprising thing is there are many problems where we have SAT solvers. These are programs which have been designed to solve the SAT problem. They actually run in a surprisingly efficient. They're surprisingly efficient for many, not all problems, but many problems that people care about. So I wrote this paper that some people have said is a useful kind of gentle introduction to SAT, linked at the bottom here. And it just goes over like how to solve some simple puzzles with SAT, like logic puzzles or puzzles like Sudoku, right? So everyone's probably played a Sudoku puzzle at one time in their life. Well, this is a classic type of problem that you can reduce to SAT, so you convert it into a SAT instance. And even though Sudoku it's not particularly a logic puzzle, it becomes a logic puzzle. You use a SAT solver on it, and then you get back an answer, right? The SAT solver will tell you assignment of the variables, which then is translated into a Sudoku solution. Okay, so what I'm going to start the talk off with is 5 examples of that, because I want to demonstrate SAT solvers are more versatile than you might at first think, right? Because Boolean logic is kind of primitive, right? You can't really express much in it, but actually it's surprising how far you can go with a SAT solver. So I have 5 to start off the talk. I just have 5 success stories that these are problems I worked on with students. The first one, so I also tried to choose like interesting problems that come from different branches of math. So the first one is the free will theorem. This is from John Conway. So John Conway was an amazing mathematician, right? He had lots of offbeat, sort of funky mathematics, and he was a genius at naming things in like catchy terms. So he had this theorem proven with Simon Koshan called the free will theorem. And so what does he mean by free will? Well, essentially he means that something has free will if there's no function which is going to predict what it does next, right? So he kind of axiomatizes the universe, uses axioms which quantum physicists believe our universe satisfy. And then he proves this theorem about free will, that if free will exists in any form, then quantum particles have free will, right? So it's this weird, almost philosophical type theorem. But from our point of view, the proof of this theorem actually relies on a combinatorial object, which I show on the right here. So there's a set of 31 particular directions in 3-dimensional space. So these dots are 31 different vectors. And he actually uses these 31 different vectors along with some axioms of quantum mechanics to prove this theorem about free will. And what we asked was, well, can we simplify their proof by coming up with a smaller set of directions than there's 31 directions? Maybe there's a smaller set of vectors. And this is unknown today. But what we were able to do with a SAT solver is to show if there is a simpler set of vectors in 3-dimensional space, there must be at least 24 of them to make the proof work, right? So we proved a lower bound on what's called a Cauchy-Specker system. And the way you do that is you reduce the problem to SAT, and you let the SAT solver search for the satisfying assignment, so of 23 vectors to this problem, and then the SAT solver says there's no solution. Okay, the next problem comes from combinatorics. So this is a famous problem from what's called Ramsey theory. And so Ramsey theory is, well, Ramsey proved this interesting theorem on graph colorings, right? So you take a red-blue edge coloring of a graph. It's going to be a complete graph. And what he proves is that regardless of, you can choose 2 integers, s and t, and you say, I want to avoid having a red clique of size s, and I want to avoid having a blue clique of size t. And Ramsey says there's no way to do that for a sufficiently large coloring, right? So you must introduce either a red clique of size s or a blue clique of size t. It's absolutely guaranteed you must introduce that regardless of the values of s and t. That's assuming you take your coloring large enough, right? So there must come a point where you're going to do that. So let's just look at an example here. So on the right, this is a edge coloring of K5. And let's fix s and t to be 3. So we're looking for triangles. You're looking for a red triangle or a blue triangle. And you can look at all triangles in this graph, and well, there's no red triangle, there's no blue triangle. Okay, so this is basically, graph is not large enough, the coloring is not large enough. But actually, if you increase the coloring just by 1 vertex, right, now you color the K6 graph, the complete graph on 6 vertices, now actually you must introduce a red or blue triangle. There's no way around doing that. And so, that takes some case-based analysis to actually show that, but this is Ramsey's theorem. So basically, the Ramsey number is to try to find the exact smallest n for which that property will hold, where you must have either a red or blue triangle. Okay, so what we did with this 2 students, which were Waterloo master students, and we used a SAT solver to actually verify 2 previously 2 Ramsey numbers, R38 and R39. These were actually previously known, but the way that they were known was by computer search code, right? Essentially, what you have to do is kind of look over. So for like R38 is equal to 28, you have to take like a 28 vertex graph and look over all possible ways of coloring the edges, right? And there's a huge number of ways of doing that, right? So you have to try to be very clever about how you go about showing every single coloring on 28 vertices must introduce either, in this case, a red triangle or a blue 8-clique. Now, we used a SAT solver to do this, and there's a reason why that this is beneficial, which is because when a SAT solver tells you something doesn't exist, it actually tells you more than that. You don't have to trust the SAT solver's word for it, right? The SAT solver will tell you, okay, this formula has no satisfying assignment, but it doesn't just tell you that. It actually produces a proof that there's no satisfying assignment. It's actually a legitimate mathematical proof where every line is a consequence of the previous lines. And then that proof can be fed to a proof verifier, and the proof verifier will check, yeah, this is actually a proof. So you're not actually trusting the SAT solver. You are trusting the proof verifier, right? But the proof verifier is actually a very simple piece of software to write, right? You just have to literally just check, okay, every line follows from the previous lines. The SAT solver is a very complicated piece of software, and anyone who's used software knows that basically all software has bugs in it, right? SAT solvers have bugs in them. So you do want to move the amount of trust that you have, ideally, to a proof verifier, which is relatively simple, rather than trusting custom code, right? So this was the benefit of this, and this work was published at ISHCAI this year. Okay, the third example of SAT applications is the integer factorization. So this is a problem from number theory, and also underlies a lot of modern cryptography. So the problem is, given a number, an integer, decompose it into its prime factors, right? Find the prime factorization. Now, at first, this seems to have nothing to do with logic, but actually, it's very closely related to logic if you think about it as a circuit, right? So on the right here, I have what's called a 2-bit multiplier, right? So you take as input two 2-bit numbers. So this would be the bits of A, this would be the bits of B, and it multiplies them together to give you a 4-bit output, a 4-bit number, which we could call the bits of that number C3 to C0. And of course, you could do this for any size numbers, right? It'll be a much larger circuit, but you could multiply 2,000-digit numbers to get a 2,000-digit number, right? You can construct these circuits. And then what you can do, this is actually a logical expression, right? You can actually give this circuit, convert it into a logical expression, give it to a SAT solver. And then the number that you want to factor, you would specify, okay, well, represent that number you want to factor in binary, and just tell the SAT solver, okay, well, these are the output bits. And then you let the SAT solver almost has to reverse the circuit, right? It has to figure out what are the input bits to that circuit. You have to also specify the input bits aren't trivial, right? Either of them can represent 1. But once you do that, if your number does have prime factors, right, then they will be found by the SAT solver. Well, there's a catch to that. The catch is that these are a type of instances that if you actually try doing this, the SAT solver does not perform very well on instances of this form, right? You can take a very large number, convert the circuit, do this multiplication circuit, convert it to SAT, feed it to a SAT solver. Once the number gets large enough, the SAT solver is going to take way too much time. It's just very, very poor way of factoring numbers. However, what we were able to show is that if you have some extra information, like some of the bits of the prime factors have been leaked, and this can actually happen in practice. The cryptographers call this a side channel attack, right? So if you have, by some different method, there's varying methods of how you might go about this, but some information has been leaked about the prime factors. If you have that information, you can actually give that to the SAT solver by just specifying, okay, I know that, okay, A0 happens to be a 1. You give that to the solver, it'll speed up the search, right? The more bits that are leaked, the easier the problem is. And we were able to outperform the best algebraic techniques, especially if you augment the SAT solver with some additional techniques like lattice reduction, which I won't get into, but it was interesting. This was work with Yamina Jani, who graduated last year and had a paper published at Isaac. Okay, the fourth problem is from automata theory, and this was work with Jeff Shallett and a student, Aaron Barnoff, who was an undergraduate student. Now he's a master's student. And here's an interesting automaton I have on the slide here. My claim is that if you run this automaton, it basically computes the binary digits of this quadratic irrational, square root 3 minus 1 divided by 2. And so you feed it the input n, and it will spit out a number, right? You do the transitions, and then the output state is the very final state. It's either going to be 0 or 1, representing the binary digit, the nth binary digit of this number. And okay, there is a catch to this. the catch is the input has to be formatted in a specific way. It's not just going to be n in a standard representation like binary. It's actually going to be n. Well, it's actually going to be 2n to the power n represented in what's called the Ostrowski representation. So you have to format your input in a very specific way. But once you do that, you feed it to this automaton. The automaton is going to spit out as output the bit, the nth bit of this quadratic irrational. So this is an interesting property. And so we actually came up with this. So Jeff has this interesting automaton software called Walnut. And Walnut can do a lot of things. One thing it can do is actually find an automaton which solves this problem, provably works for all n. Right? It provably computes all the digits of this quadratic irrational. And it happens to have 12 states. Now what we did, so what we wanted to do was minimize that automaton, right? Find, is 12 states optimal, or can you do it with 11 states or 10 states or a smaller number of states? So we encode the problem into SAT, let the SAT solver try to solve it. It's able to prove there's no 10-state solution pretty quickly. And then for the 11-state solution, it actually returns the automaton on the slide here. So it actually finds an 11-state solution. Now, the catch is we can't actually prove this automaton works for all n, because the way you construct the instance is you have to tell the SAT solver, okay, for n from 1 to a million, right, the first million digits have to be these specific values. And then the SAT solver, okay, takes that into account, into the logic formula, and then spits out a solution which works for the first million digits. So it's possible, although we argue that it's unlikely, subject to some heuristic, it's possible that this automaton computes something wrong after the millionth digit point. But it's we argue that's extremely unlikely. So we do think that this is actually the minimal solution for this particular problem. Okay, the last success story before I get into an actual case study is, I think this will be, so Rado numbers. I think this might be interesting to this audience because it's kind of a combinatorics on words type problem. This is also a problem from Ramsey theory, but it's not coloring graphs, it's coloring integers. Okay, so what we're going to do is we're going to color the integers from 1 to as far as ideally you want to color all the positive integers. And the constraint is you want to avoid coloring solutions of an equation, just a linear equation, all the same thing. So as an example, let's say the equation E here is x plus 3y is equal to 3z. So a solution of this would be x is equal to 3, y is equal to 1, z is equal to 2. Right? So 3, 1, 2 is a solution. So what we want our coloring, I think I lost my audio, but we want the solution to be 3, 1, 2 to not be all colored the same way, right? So they can't all be colored red, for example. Okay, so what we have here is a coloring of the integers from 1 to 26, which avoids monochromatic solutions of E, right? And actually what you can show with some case-based analysis that if you go one step farther to 27, then you actually must introduce a monochromatic solution of E. And SAT solver can actually compute these Rado numbers actually quite quite large ones. So for example, the equation 15x plus 15y equals 8z, the SAT solver can actually prove that that Rado number is actually 97,875. So it does this by finding a coloring from 1 to 97,874, which avoids all solutions of monochromatic solutions of E, and then it's actually able to show the non-existence of a coloring that avoids all monochromatic solutions of E of the integers from 1 to 97,875. Okay, let me just stop and make sure. Is there any questions about anything at this point? And everyone can hear me? So yeah, I lost my...
We can still hear you okay.
Okay, perfect. I lost my audio, so I was just worried, but as long as you can hear me, then I took my headphones off. Okay, so what I want to do is now get into an actual problem which has a kind of combinatorics on words flavor and a Ramsey theory flavor, and also a kind of a geometry flavor. So it's going to be talking about paths. And we're going to use a SAT solver to tackle this problem. So this is a problem on northeast lattice paths. So what's a northeast lattice path? Well, it's just a path starting from the origin where at every step you either move one step north or one step east. Right? There's no backtracking, there's no diagonal move. So it's always just one of those two steps. So you can think of this like, a binary word wouldn't, an n-step path would be equivalent to a binary word of length n. And what we're going to do is avoid making k collinear points on this path. Okay, so k is going to be a number that we fix in advance. And so an example, let's say k is 3. We want to avoid 3 collinear points. And let's say our path is moved up, moved right, moved up. Okay, so now we're here. And actually, what would happen at this point is you cannot actually make a further step, because if you moved up again, you would introduce 3 collinear points on a horizontal line, right? The 3 blue points here, or rather a vertical line. Or here, if you move to the right, you would also introduce 3 collinear points, but they'd be on a diagonal line, right? The line y equals x. So at this point, there's no way to actually proceed, right? So what actually, this was a problem of Tom C. Brown that he proposed, and then he actually gave a non-constructive proof showing that regardless of the value of k, you must introduce k collinear points, right? There's no way to make an infinite path that avoids k collinear points. Okay, so it has to be done regardless. Even if you want to avoid 1,000,000 collinear points, eventually your path is going to have 1,000,000 collinear points. Okay, so the original proof was non-constructive, but then there's an effective version of the proof which came out several years later of Gerver and Ramsey. And the theorem, okay, is shown here, right? If your path is of length 2 to the 2 to the 13, and then times a quartic function of k. So this is a pretty fast-growing function. It must pass through at least k collinear points, right? So this gives you a bound on, or a guarantee that you will introduce k collinear points if you have a path of this length. Now, this is an extremely fast-growing function, right? It's a very loose bound. In fact, it's humorously loose, because let's just take the example of k equals 2. Well, if k equals 2, the bound says, well, any path of 2 to the 2 to the 13 must contain 2 collinear points. Well, that's about 10 to the 2,500. That's way more atoms than there are in the universe. And if you think about it, right, if you're trying to avoid 2 collinear points, well, as soon as you take a single step, you've introduced two collinear points, right? Let's just move up. Well, the start point and the end is now 2 collinear points, right? So it's extremely loose bound. So but it's in effect, it is a provable bound. It's definitely not a tight bound. So what we want to do is actually try to find tight bounds, right? See how far you can go for a specific value of k. So let's say k equals 3. So this one's actually relatively easy to show, because if k equals 3, you want to avoid 3 collinear points, you can never walk the same direction twice in a row. If you walked up twice, that would introduce 3 collinear points, or if you walked right twice, that would introduce 3 collinear points. So the best way to avoid introducing a collinearity then is to alternate, right? You go up, right, up, right, up, right, or right up, right up, right up. Well, either way, after 4 steps of that, you introduce a collinearity, as we saw here, right? So essentially, the longest you can go is 3 steps, and then on the 4th step, you're absolutely guaranteed to introduce a collinearity. And so this was actually, this function, this optimal counting function, was actually added to the OEIS by Jeff Shallett, 2013. So essentially here, you'd have k equals 1. Well, in that case, you can't have a path at all. K is equal to 2, then you can take 1 step, and then you're guaranteed to introduce a collinearity. Then the one we just showed was k equals 3. You take 4 steps, and you are guaranteed to introduce a collinearity. Now, the next one would be k equals 4, and that would be 9 steps. And you're guaranteed to introduce a collinearity. And so here is an optimal path for 9 steps, right? It happens to be up, right, right, up, right, right, up, right, right. And then on the 8th step, you're okay. You haven't introduced 4 points on a line yet. But on the 9th step, regardless of what you do, you will introduce 4 collinear points. And here's just one example of that, right? So you have 4 points on a line. For k equals 5, you have this what kind of looks like a semicircle curve here. And it's 28 steps you can walk without introducing 5 collinear points. And then on the 29th step, you must introduce 5 collinear points. And here is an example of 5 collinear points on a line on the 29th step. And then here's where things start getting even a little bit more erratic, right? For the solution for k equals 6 is this red line. So it has 97 steps on it. And it starts to become kind of a windy, erratic path, right? Because you want to avoid you're trying to avoid straight lines, essentially, right? So you're kind of like curving around all over the place, trying to avoid doing that. But eventually at the 97th step, you must introduce a collinearity. And indeed, you have, actually in this case, 2 collinearities, right? On the 97th step, you have these 1, 2, 3, 4, 5, 6 orange points. They're all in a line. And also the 6 blue points are in a line. Okay, so that's the state of what we know right now, right? So these were actually computed by Jeff Shalett using APL. This was, back when he introduced the OEAS, it into the OEAS, he computed the first 6 values of this function, right? So I'm just kind of changed the indexing, but I'm going to define AK to be, the smallest integer n, where if you take an n-step path, you must introduce k collinear points. So we have a lower bound on k equals 7 computed by Jeff. So he found a 260 point path, and without introducing 7 collinear points. So there's no proof that that's optimal. So what I want to do now for the rest of the talk, now that I've introduced the problem, is to show us how we could actually solve this problem, or at least try to make progress on this problem with an automated reasoning approach like a SAT solver. So we're going to encode the problem into SAT, and then we're going to let the SAT solver find paths which avoid k collinear points, and also prove the optimality of those paths, right? So you're able to prove that any path of a given length must contain k collinear points, right? So that's typically the harder thing, right? Finding the solution is typically easier than proving the non-existence of a solution. So the SAT solver can do both. Okay, so the thing about SAT is that it doesn't have concepts like paths, right? It doesn't even have a concept of an integer. So you have to find ways to massage your problem into a logical framework, right? So all the variables must be true or false, right? They have to be Boolean. So in this case, it's not too bad because we can represent paths with just a collection of Boolean variables kind of aligned out in a grid. First of all, we're going to fix k, the number of collinear points to avoid. We're going to fix n, the number of steps in the path. And then we're going to encode the existence of a length n northeast path. And that's going to use a bunch of variables here. So let's say n is 4, right? These are all the kind of points that you could reach with 4 steps, right? Let's say we start at the origin 0, 0. Well, if you went up 4 times, you go to 4, 0. If you went right 4 times, you get to 0, 4. And then if any other path with 4 steps would be somewhere in this triangle. So these are kind of the relevant variables that we're going to use. And we use this vxy, which is going to be basically a variable which denotes if xy is on the path or not, right? So if vxy is true, that means that variable is on the path. And if vxy is false, that means the variable is not on the path. Okay, so you just define this collection of variables in this triangle. Now we're going to be able to represent paths of length n. Now, what we have to do is encode a path of length n using logic. So it's a little bit different than programming, say, in Python or something like that, where you have commands like looping and things like that. In SAT, all you have are constraints. You just have to tell the solver what a solution would look like. What are the properties that a solution satisfies? And so let's give an example of that. So let's say xy is a point somewhere in the path, let's say the middle of the path to make it simple. Well, if xy is on the path, then you either have to take the next step is either upwards to the north or rightwards to the east. So if xy is on the path, then the next point that's also on the path is either xy plus 1 or x plus 1y. So in logic, you would represent that as an implication, right? Vxy implies either x plus 1y is on the path or x, y plus 1 is on the path. And this is something that is now an expression in Boolean logic. Now, of course, you also want to say you can't step both directions at once, right? This is not like a quantum problem where you can have a superposition of going north and east at the same time. You would never step both ways, right? So if one of these is true, the other one has to be false. So you have these. You'd look at these two variables and say, well, okay, if they can't both be true at the same time, right? So you would express that as not x plus 1y. And it can also be the case that x, y plus 1 is true at the same time, right? So both of these can't be true simultaneously. That tells you that if you take a step, well, it's definitely in one direction. And then the last one here is kind of just, if you know that x, y is on the path, then you must have come from somewhere, right? You must have come from the west or come from the south. So the previous step must have been, if x, y is on the path, the previous step was either from x minus 1y or x, y minus 1. So you also have a constraint like this. This is assuming that you're not at the beginning, right? Assuming that you're not at the actual origin 0, 0. You must have come from somewhere. Okay, so these are just three constraints which then encode basically the existence of an NE path. And to actually write them in a format that the stat solver can read, you convert them into what are called clauses. So clauses are just, you remove the implications, right? And you write them as just an expressions using not and or, right? So you have, each one of these is a clause. It's a logical disjunction of variables or negated variables. So essentially what we're doing is we're writing the formula in what's known as conjunctive nominal form, if you've heard of that. Okay, so this is how this is how you give input to stat solver. You just give it a bunch of clauses. And so you can convert your logical expression to clauses, and then you give clauses of this form for all the relevant values of x and y in the acceptable range for n set paths, right? And then you give this to the stat solver. We're also going to specify that the origin point is true, right? So v0, 0 must be true because that's by fiat, right? It's the first point on the path. So you start it off like that, and then the constraints are going to, if you actually give this to a stat solver, it will give you back a valid NE path, right? It will give you back a satisfying assignment, which we can translate into a path. So we've kind of avoided the hardest part of the problem, right? Which is now the collinearities, right? We want to avoid having k collinear points on a row. So the simplest case is, let's say, k vertical points, right? K vertical points is the first one we'll talk about because this is the relatively easy to encode. Because if you think about it, if you're going to avoid k vertical points on the path, then you have to avoid stepping upwards k minus 1 times in a row. Because if you stepped upwards k minus 1 times in a row, that is going to introduce k collinear points, k vertical points, right? They'd all be on the same vertical line. So essentially what you're saying is if x, y is on the path, then the point which is k minus 1 steps above it, which is x, y plus k minus 1, that also can't be on the path. If both of those 2 points are on the path, you've introduced k vertical points. So what you do is you just tell the solver, well, okay, don't do that, right? If x, y is on the path, then it cannot be the case that x, y plus 1 minus, x, y plus k minus 1 is also on the path, right? So that is given to the stat solver, and the stat solver will never give you back a path that has k vertical points on it. You can do the same thing for horizontal points as well. Okay, but this is the simpler case, because the more complex case is you have to avoid any set of collinear points, right? So you want to avoid, you have a path where there are no k collinear points at all, and this might, the variables on the line might be a line which has a slope of y equals x, y equals 2x, maybe even y equals a half x. So the slope of the line might be even a fraction. And so there's lots of lines you have to consider. But what you do now is, well, I want a constraint like this. I'm going to think of the variables vx, y not as true and falses, but as zeros and ones. Just a simple, 0 represents false, 1 represents true, but I represent them as 0, 1, so I have this nice summation notation. And then I want to say, okay, I'm going to sum over all the points on a line, and then I'm going to say there cannot be k or more points on that line. So I just have to kind of it's a kind of a sum for every single line that could be in the all possible lines here. So you have to go over all possible slopes, all possible y-intercepts. So m and b here might be fractions. Mx plus b has to be an integer, though, right? Because the variable vxy, x and y are integers. Okay, so you sum over all of your points on that line, and then you say that the number of points on that line must be less than k. Because if it was k or greater, you'd introduce k collinear points. Now, the problem here is that this expression is a constraint, which is called a cardinality constraint, because it's not a clause, right? It's kind of, you're saying you have this set of variables, and at most k of them are true, but you can't represent that as a single clause, which is in Boolean logic. So what do we do? It seems at first like you can't use a stat solver for this problem, but the thing is, stat solvers are very flexible. You can encode constraints like this into Boolean logic, and I'm gonna, in fact, there's many ways to do it. People write papers just on cardinality encodings. I'm just going to give you one way here, which is one of the relatively simple ways. It was from about 20 years ago of Carson Sines, the paper cited at the bottom. So let's say we want to encode this constraint. We have n variables that we want to specify, let's say x1 to xn. We have this set of n variables, and we have at most k of them can be true. So let's say the set of variables is called L. And the trick here is we're going to define a new variable, skn, which represents at least k variables of L are true. Okay, so this skn is going to be a new variable that doesn't appear already in the set instance. And the trick that makes Sines' encoding work is that we can kind of define skn inductively. We can define it in terms of not L, but in terms of L primed, which is just L removing the last variable. So I'm going to define it in terms of L primed, because this is going to allow me to use induction. All right, so in induction, you have base. So there's actually 4 cases to consider, 2 base cases and 2 inductive cases. The base cases, you can just convince yourself that these are obvious. S0j is always going to be true, because there's always going to be at least 0 variables true in any set. And then Si0 is going to be false if I is anything positive, because you're essentially now looking at, in this case, you're looking at the empty set, and you can never find k variables true in the empty set unless k is 0. Okay, so those are the 2 base cases. Now, in the inductive cases, there's 2 of them. The first one is saying if at least k variables in L primed are true, well, then you know it for certain that at least k variables in L are true, which means skn is true, right? Because L primed is a subset of L. So if at least k variables of L primed are true, it's definitely true that at least k variables of L is true. So then you can derive skn. And then the second case is if xn is true, and then you have at least k minus 1 variables of L prime true, well, then you must have at least k variables of L true, right? Because xn is not in L prime, but it is in L. So you actually are able to then prove, in this case, also skn is true. Okay, so it's this, it's a simple kind of inductive way of counting. And then, the thing about these 4 constraints is that they can be encoded into logical constraints at the bottom here. Okay, so, and you're not introducing too many new variables for this. You're essentially introducing k times n new variables. So it is a reasonable way of going about encoding a constraint like this. Okay, so the last thing I want to talk about before I talk about the results is symmetry removal. This is an important thing to consider often in combinatorial problems. It turns out to be very important, because essentially a lot of combinatorial problems have symmetries, right? There's basically a set of solutions which are all the same up to isomorphism. In this case, there's an obvious symmetry, essentially reflecting the path around the diagonal, right? If you go, you might as well just assume that the first step is upwards, right? Because if there was a solution where the first step was to the right, you could flip the polarity of every single step, right? You switch all the east steps to north steps and vice versa, and then you would have any solution with it. The first step to the east would then be converted into a solution with a step to the north. So you might as well just assume you step north first. It kind of cuts down the search space by a factor of 2. And so this is called symmetry breaking, right? And it's easy in this case to encode this into the SAT instance. You would just say, okay, well, these on top of 0, 0 being on the path, also 0, 1's on the path. And this is going to imply that 1, 0 is not on the path. So that we're going to assume that we've done that. Okay, so now we get to the cool diagrams. So here is what I call a reachability diagram. So I've fixed, this is for k equals 4. So I'm avoiding 4 points on a line. And I've assumed, like I just said, that the first step is always upwards, right? So we can't actually make it to 1, 0 here. So the red essentially means you cannot actually make it to that point, or the green means you actually can make it to that point without introducing k collinear points on a line. And the way that I found this diagram was just to feed a sat solver. Every point on the grid was actually a sat instance. And I just, for that sat instance, I said, okay, well, 0, 0 is on the path. And then whatever point, let's say we go here, then this point would be on the path too. And I try to let the sat solver find a way from here to here. And if it's able to find a way, it gives me a satisfying assignment, giving me a path, and then I color it green. And if I tried to go here, the sat solver tells me it's unsat, and then I color it red. Okay, so essentially what the farthest you can get is here. This would be an 8-step path, and there's actually multiple 8-step paths which reach the farthest you can go. And then once you take 9 steps, you can't go and you can't do it. And this is basically instant, right? The instances are fast enough that the solver, even though there's many calls to the solver, it just runs immediately. But now let's actually increase the value of k. And so now in this diagram, you have what looks like a leaf here, and there's a little bit of jagged edges on it. And this took around under a second, so it was still very, very fast, right? And again, I just had to call for every square in the diagram. It's a sat call. The red calls are unsat, meaning there's no solution, and the green calls are sat, meaning there is a solution to that point. So the farthest you can get is over here. And then the really cool looking one, k equals 6, looks like a lobster claw or something. So this one is a bit surprising when I first saw it, but it kind of makes sense. This took about an hour and a half. And so you can see there's like 2 kind of paths that take you the farthest, but you can't get to pass in between them. And I think the reason for that is essentially there's a lot of points along the line y equals x, right? Essentially you can only cross the line y equals x in your paths 5 times, right? Because the 6th time you try to cross it would introduce a collinearity on that line. So that essentially is limiting the number of times you can cross the diagonal. So you can make it farther if you kind of stick to one side or the other rather than trying to cross the diagonal. Okay, so this is for k equals 6, right? And you can see that the solver is relatively efficient, right? If you tried to do this by hand, it would probably be slower than the sat solver unless you took really tried to optimize it significantly. Okay, so now k equals 7. So this is the one that we don't have the solution to, but what I did was I at least found some upper and lower bounds to the path, represented by the green lines here. And then I found a path. So the blue line is an actual path avoiding 7 collinear points. So the red instances are all unsat, and most of them are easy to show. The hardest ones are the ones that are around this green line, right, on the boundary. The green points on the boundary are the solver was able to find a solution to that point, avoiding k collinear points. And the white ones I just, I didn't run because there's too many of them. So, it's a cool sort of, I don't know what the actual solution is, but you can see it's, how the solver was able to make progress, pretty far, substantially far. This is a 316-step point path. And Jeff had gotten to 260, I believe. And so what was the compute time for this? So the compute time for the upper and lower bounds was altogether 195 days. Right, so this was kind of just run in sequence. Once it finds a solution, you go on to the next one. And then the point itself, finding the blue line, right, the actual the path that avoids k collinear points, I actually made a 310. So I fixed k to be 7, n to be 310, and then I generated this huge sat instance. It's pretty large, and then I split it, right, because it was so large. Solver would take a long time to try to solve it, so I split it into 131 subinstances. I won't get into the details exactly how that is done. Essentially, it's just you take a variable, some variable which looks good, subject to some heuristic, and you just split on it. You say, oh, set this variable true, and that's one instance, and set the variable false, that's another instance. Okay, so now you have two instances. You split the problem into two. And then you just do that kind of iteratively until you get 131 instances. And then you have 131 instances which are all disjoint, and you give them to 131 different SAT solvers on a cluster. And I ran each instance for 2 days. And then what actually happened was 130 of the instances timed out. After 2 days, they were still computing. It didn't tell me either SAT or unsat. They were still going. And you have to cut them off at some point. But one of the 131 instances produced a solution, which was a 310-point path, which avoided 7 collinear points. And interestingly, that path could actually be extended by 6 steps. So it actually gave me a 316 point path. And here it is. So the red line is, the kind of lightning bolt looking thing in the middle. That's the 316 points. And I verified that there aren't 7 collinear points on this path, which, so the encoding was correct, right? The SAT solver did give me back a valid solution. And then also I verified, I looked how many times are there 6 collinear points on this path. And the black lines you see here are every time there was 6 collinear points on the path. So, it happened quite frequently. And this is basically why the problem is difficult, right? Because there's so many possible lines to avoid, right? So trying to make progress, you can't extend this path any farther because you're going to hit one of the points on one of the black lines, right? Because there's just so many of them, right? So it's a very constrained search space. Okay, but the problem is it's a very large search space, right? So we weren't able to actually, or at least I wasn't able to get the exact value. So the best was 316 steps I found, or 316 points. So that means the lower bound is at least 317 and possibly higher. But, and this was all done, with not too much compute time, right? Everything up to 6 was an hour and a half. And then this one took, around a year of compute time altogether. Okay, so this is the summary on, I wanted to kind of showcase that SAT solvers are good for combinatorial problems, right? Often like combinatorics on words, these sorts of things where they're discrete, right? So if you can encode your problem into logic, and there are many ways to actually do that, right? Once you think about it, there's surprisingly a surprising variety of type of problems that can be encoded into logic. So the master student I mentioned, Aaron Barnoff, he's actually working on improving this bound. So maybe we will, maybe there's more to come on this problem, and so hopefully we'll maybe we can actually figure out the value of A7. Okay, so that's all I had. Thank you. I'll take questions.
Thanks a lot, Curtis. Does anyone have any questions? Oh, Hajime.
Thank you for nice talk. So you've mentioned applications for Ramadan theory. I'm interested in the such of applications. I'm curious about the fundamental numbers. That means coloring of 1, 2, and so on, and find arithmetic progressions of length scale. So it's possible to apply for such a problem?
Yeah, is this the van der Waerden problem?
Yeah.
Yeah. So in fact, a lot of the van der Waerden numbers that are known, I think, were computed with SAT solvers. So yeah, so look at so Tanbir Ahmed's work, and I think the value of the W26, I think, was computed with a huge cluster of SAT solvers.
Thank you.
Does anyone else have a question? So I was wondering, you showed us that ridiculous bound from the Gerver-Ramsey paper. Do you have any sense of what the correct function should be there?
Not really, right? Because essentially what we have, I don't think, I mean, yeah, I'm not sure if there's any improvements to that bound, but it's definitely very, very loose. And if you look at the values that are known, it's not too fast growing, right? It looks like something like quadratic or something. So, but yeah, I really don't have a good sense of that.
What sort of ideas is your student sort of exploring to speed this up or to go further?
I mean, parallelization is going to be a big one, right? If you can find a way of doing the split, and Marian Hule has done a lot of work on this sort of thing, this Cuban conquer paradigm, where the actual splitting the problem into two actually has a big impact on the running time, right? You kind of want a split which is kind of even, right? Because oftentimes when you split in a variable, one of the two subproblems is going to be much easier to solve than the other. And surprisingly, if you read Marian's papers, like the Sure number 5 paper, right, he gets super linear speed ups. So he has 1,000 processors, he splits it into many cores, and then he gets more than 1,000 times speed up. Just the fact that of the splitting itself lets the SAT solver solve the problem faster than it would have if you didn't split it, which is fascinating, right? So the splits actually can have a huge impact. So things like that, right? But it's hard to say really what I'm I've worked in SAT for like 10 years, and like I'm still surprised by SAT solvers, like what type of, you get some intuition of the good encodings, but still there's still kind of mystery of what are the best SAT encodings.
Thanks, Stepan.
Very interesting. I wonder, I have maybe it's not a really question, it's a kind of a reflection. It seems to me like that using this encoding into SAT problem, now it's kind of avoiding the, like, I would say like a real nature of the problem, right? Which seems to be like numerical, or let's say, I think it's about some balanced factorizations, I think, right? That's my feeling, right? And so do you think that it can eventually, like, I think that is a trade-off, like between this kind of blind approach and the insightful approach,
Mm-hmm.
because I think it has something. You actually don't know what you are doing, but you are just looking on some optimization, which is not really, and so on. That's it.
Yeah, you're cutting out a little at the end, but I got your point, and it's a good one, that that's a SAT solver is a little bit like a generic tool, right? And it's a good generic search procedure, but oftentimes there's knowledge that the SAT solver doesn't know about. Right? In fact, that's been a huge thrust of my research, is actually augmenting the SAT solver with this kind of domain-specific knowledge. Right? So often in a computer algebra system, for example, they have functions which will do things that the SAT solver has no way of doing. Right? And so what you can do is augment the SAT solver with extra information. Right? So as it's running, you can kind of feed it facts about the search space that it wouldn't otherwise derive. And so, I wrote a lot of papers on exactly this problem, that the SAT solver is a great generic search tool, but oftentimes the problem's not generic, right? There's some extra structure that you want to exploit. And so, yeah, indeed, there's many cases of that where if you can feed the right information to the SAT solver, it'll actually it'll be way more efficient.
And in this particular case, do you think that?
Yeah, I mean, that was one of my first instances of why I wanted to look at this. That's something we're going to explore, because there's not any good theorems that you can really apply, right? Like, at least as far as I know, there's no. What you want is like some kind of like a theorem that someone has proven, which will constrain the search space, right? And I don't know of any in this case, but ideally, that's what we'd want to do.
Is my intuition correct that the theorem should say something about decompositions?
About what?
I would say number decompositions, like the number of decompositions which have some.
Possibly. I mean, yeah, I have to think about it.
Hmm. Yeah.
But yeah, I mean, the nice thing about using like a computer algebra system is it's just so there's so much mathematical functionality there, right? There's so many functions that you could potentially use. And so there's often, many ways to speed up a solver by adding extra information.
Oh, Weeb.
Hi. Thanks for a beautiful talk, Curtis.
Thank you.
I have a very ignorant question. You're talking about the set solver all the time in a very generic way. What is, in your point, from your perspective, the set solver? Is there a generic one? Is there one that you always use? Is there a dependence on the type of problem? Can you say something about this?
Yeah, that's a great question, and there's no one right answer. They have a SAT competition every year, actually, where they kind of compete for the fastest solver on like a collection of like new benchmarks. And so you can kind of look at the SAT competition output. Like one of popular solvers called KissSat. Uh, there's MapleSat. There's Caticle. There's these solvers that kind of are often at they've won awards. And yeah, so typically you just use one of the recent solvers, and you might try a couple of them, right? Like for actually a good library to get started with is called PySat. It's a Python sat solving library, which actually has a bunch of solvers built in. So you can just say solve this with this solver, and sometimes there are a specific problem where one solver will outperform the others, but it's very random. Like it's not. You basically just have to try it and see.
Is there, as a continuation on the previous question, is there work being done on actually integrating the set solver with a computer algebra system so that, like in your two of your examples where you want to do lattice reduction or where you want to do some factorization using bits, that makes it easier to do that or actually optimize things? I mean, it's also in line with the question, the previous question by Stepan, right? Because
Yeah,
you use knowledge that other people have and other algorithms.
yeah. So I actually did work at MapleSoft, who develops a computer algebra system, and one of the things I did there was improve the functionality of the SAT solver. Some actually Maple commands will actually use it internally. As far as augmenting the SAT solver with domain-specific knowledge, Caticle has a nice interface now. It's called Ipacer Up. So the solver Caticle will actually allow you to inject domain-specific facts as it's running.
Okay, thank you.
Thank you.
Stepan?
Oh,
May I have one more comment?
yeah,
Yes,
yeah.
of course.
From the combinatorics of words point of view, I think if you have just correct me, but I think it's quite obvious that if you have an abelian power in a binary word, that means that actually you have a progression, that you have a collinear point, but they are also of the same distance. Is that correct, right? So actually this is maybe some link, right, that you have to avoid words which have probably arbitrary abelian powers.
Okay.
I don't think that it helps very much, but it's just an observation.
Yeah, those are the types of observations that maybe the solver wouldn't otherwise deduce, right? So if there's a way to encode that into SAT or to use a computer algebra system to tell the solver as it's running, it can speed up the search, right? So yeah, I'm not a combinatorics on words person really, right? So I don't, maybe it would be good to talk about that after. But yeah, thank you. Those are the types of things that we'd want to encode.
Are there any other questions for Curtis? If not, thank you. Thank you very much, Curtis.
Thank you for the invitation. Yeah, no, it's been fun.
Yeah, it was a great talk. Thank you everyone for coming out, and we'll see you all again in 2 weeks for the next talk. So until
Thanks.
then, bye for now. Bye. Bye, everyone. Bye, Curtis.
Bye.